Hello, good people. Today we are talking about some very, very important topics like why the sky is blue and why sunsets are red and why clouds are white and why pools are that weird cyany color. Um, we're going to start today by talking about why the sky is blue, and then we'll move through each of these questions. Now, if you wanted to answer 3 of these questions, you could answer them with one word, and the one word that you would use to answer them is the word scattering. Here's one of the big ideas for today, is that light can be scattered. It can be thrown around in all different directions. We'll start by talking about why the sky is blue. Now, our atmosphere, whoa, I don't want that there. Our atmosphere, I'm going to make this big, is mostly made up of oxygen and nitrogen. And the oxygen and nitrogen molecules are very, 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 very small. Now, there's a really great analogy that I love to use when it comes to talking about light scattering that really relates back very, very nicely to our sound unit. And it's an analogy that I heard when I first learned about why the sky is blue, and it has been just oh so very helpful to me. Here's the idea. Do you remember when we talked back in the sound unit about how all things have a resonance frequency? Pendulums have a resonance frequency. Springs have a resonance frequency. The table in front of me has a resonance frequency. All things have a resonance frequency. Your guitar has a resonance frequency. The cello has a resonance frequency. And we talked about how if you shove something back and forth at its natural frequency, at its resonance frequency, then it'll shake back and forth with an even greater amplitude. And it'll take the frequency of that sound, if it's a sound wave, it'll take the frequency of that sound and it'll vibrate back and forth even stronger, and then it'll throw that sound out into the world. Well, it turns out that when it comes to molecules like nitrogen and oxygen, you can think about them as also having resonance frequencies, but having resonance frequencies of light. Now, this is true when it comes to sound, that if I had a really large handbell and a really small handbell and I rang them both, the one that's the really big handbell, when I ring that one, it would go dong. But the one that's a really small handbell, when I ring that one, it would go ding. And so we know that things that are larger in general tend to have lower resonance frequencies. Things that are smaller in general tend to have higher resonance frequencies. Now, this same analogy applies to molecules. Nitrogen and oxygen, N2 and O2, which make up most of our atmosphere, they are very, very small molecules. N2 is just 2 little nitrogens, and O2 is just 2 little oxygens. Not a lot going on. Because of the arrangement of these atoms, you can think of them as having very high-pitched resonance frequencies, like a little high-pitched bell, a teeny tiny bell. So the small ones have high resonance frequencies, the big ones have low resonance frequencies. Now when it comes to resonance frequencies of light, here's what I really mean. I mean that when a light wave comes in, if that light wave has a very high frequency, then that high frequency light will get absorbed by one of the electrons and it'll vibrate back and forth like crazy. And when it vibrates back and forth, as that little particle is moving, it's going to throw a new photon out into the world in some random direction. The same way that if you strike a chord on a guitar and the body of the guitar resonates, it's going to throw the sound out into the room. The same thing is going to happen with a little molecule. If you hit a little oxygen molecule with a frequency of light that's a very high frequency of light, and it hits that little oxygen molecule, the electron inside will vibrate back and forth like crazy, and then it'll send out a new photon in a random direction and throw that photon of light out into the world. Because nitrogen and oxygen molecules are so small, you can say that the resonance frequency of a nitrogen molecule or an oxygen molecule would be a very high frequency, a frequency like the color violet or like the color blue. This means that when white light comes from the sun and hits nitrogen and oxygen molecules in the atmosphere, that white light we know is made up of red light and green light and blue light. It's made up of all different frequencies of light. When that light hits the nitrogen molecule, the red light will just kind of pass on through and the green light will just kind of pass on through, but the blue light or the violet light, that really, really high frequency light, will cause the little electron in the nitrogen to go wee, and it'll go like crazy, and then it'll release a little photon out in a random direction. And if all the little nitrogen molecules all over the world are dancing to the rhythm of high frequency light, and they're all throwing out these high frequency photons all over the place, then when we look up at the sky, we see high frequency photons everywhere. We see the color blue all over the sky because each of these little nitrogen molecules, each of these little oxygen molecules is scattering the blue all over the place. This is what we mean by scattering. It means a light photon comes in, hits a little molecule, and that molecule throws out another photon in another direction because it happens to be close or similar to the resonance frequency of that particular atom or that particular molecule. The sky is blue due to scattering of high-frequency light from these little nitrogen and these little oxygen molecules. Now, I don't know if you've noticed this before, but the sky isn't always the same shade of blue. This is something that I noticed when I was a kid, and it kind of bothered me. Like, I look straight up into the sky, and I see that the sky directly above me is a very, very dark blue. But then if I look out on the horizons, I would see along the horizon line that out there the sky was actually a very pale blue, and out there also the sky was a very pale blue. So I saw that along the horizon it was very pale blue, but just above me it was a very dark blue. And I noticed other things too. When I went to college, I started here in Denver. I grew up here in Denver, but when I moved out to Illinois for school, I noticed something. I noticed that even on the clearest day in Illinois, the sky in Illinois was less blue than the sky in Colorado. Even on days when there were no clouds, it was still kind of a paler sort of blue in Illinois than it was in Colorado, and I thought that's very mysterious. And then I also noticed something else. And next time you go skiing, pay attention. The next time you go skiing up in the mountains, look at the sky. The sky looks like a deeper blue or a more indigo-y kind of blue, a much deeper, darker kind of blue in the mountains than it does here in Denver. And I thought this is so interesting because the sky is blue, and it's blue because of this scattering, but what exactly differs between Colorado and Illinois? What differs between when I'm here on the ground versus when I'm up in the mountains? And what differs between the light right above me and the light from the edges, from the horizon of the sky? The answer is that the blue that you see depends on both the number of particles that that light has to travel through and also the size of the particles that that light has to travel through. Let's take a look at an example. We'll start with my first issue, which is what happens when you have light that's directly above you versus light that's on the horizon line. Why are those two different shades of blue? Well, let us draw an image here. Here is the ground or the earth. Here is you. And I do have to say that you look quite fantastic today. When you're looking at the sky directly above you, here's the sun directly above you. When you're looking at the sun directly above you, the light from the sky directly above you has to travel from here down to here to get to your eyes. And so the light from the sky directly above you has to travel through like this many air molecules to get to you. But if you were looking at the sky over here on the horizon line, right here, that light to get to you has to travel a much greater distance. So it has to travel through that many molecules to get to you. And so this light here has to travel through less, this light has to travel through more, and additionally, these particles down here closer to the Earth are a little bit bigger than the particles up here because the heavier molecules will sink down towards the bottom. And so you have bigger molecules here, you have bigger particles, and you have more of them. Here the light just has to travel through this many, here the light has to travel through this many because it has to go a much bigger distance. Here's the main idea. The more particles that the light has to travel through, the more scattering is going to happen. So when it travels just this distance, well, a lot of the violets get scattered and a lot of the blues get scattered as well, and so they get scattered throughout the sky. But when it has to travel this distance, a lot of the blues get scattered and also some violets or a lot of the greens get scattered. Some of these lower frequencies also get scattered. So it's mostly blues, but then you get some scattering of some other particles, or some other frequencies, excuse me. If you get scattering of just blues, that sky will look very, very brilliantly blue. But if you're getting scattering of blues and also some greens and maybe a few yellows, then the sky is going to look like a less blue. It's going to look more of a pale blue as those colors mix together and get closer and closer to white. So light, the sky along the edges of the horizon, is going to look a much paler blue because that light has to go through so many more particles, and so there's so much more scattering, versus the light that's directly above you just has to go through a few particles, and so only the blues and the violets get scattered. That is a little bit about why the sky is different colors depending on if it's on the horizon or straight up above you. You could see how this would apply very nicely to your elevation. If you're changing your elevation, if you go up into the mountains, well, you literally just put less atmosphere between space and you, which means there's less atmosphere to do scattering of more frequencies, which means only the violets and the blues are getting scattered. And really, it's mostly violets up there. Just even less blues are getting scattered. Mostly violets are. So when you're up at a higher elevation, all of those blues all the violets get scattered and some blues get scattered. And so the blue of the sky up at higher elevation is an even deeper blue, because there are less other frequencies getting scattered, and it's really only those violets and those blues that get scattered. So you see a nice deep blue sky up at high elevation. This is also related to what happens when you go to another state like Illinois. Now, here's what I noticed is that the summertime sky in Illinois was way different than the summertime sky in Denver, because the summertime sky in Illinois was just a little bit whiter, just a little bit of a pastier kind of blue. Now, this is because Illinois is a much more humid state. There's much more water molecules in the air. And if there are much more water molecules in the air, well, water molecules happen to be a little bit, if you have like full-on water droplets in the air, well, these full-on water droplets in the air are going to be a little bit larger than just the plain old ordinary nitrogens and oxygens. And so they'll scatter even more frequencies. Because they're a little bit larger, their resonance frequency, or the frequencies that they scatter the best, is a little bit lower. And so they'll scatter colors like greens and yellows. And so then it's not just the blues that are getting scattered, but it's the blues and some of the greens and some of the yellows. And so that sky will look a little bit of a pastier, kind of whitish kind of color. So how blue the sky is depends on what kinds of molecules are in the air and how many of them there are, how many that light has to travel through in order to get to you. Generally, the more particles that it has to travel through, the more scattering that you get. This also relates to the color of the sun. You know that if we go up into outer space and we were to look at the sun would be a very pure white color. But if you're down on Earth, you know that no little kid ever draws the sun as white. No, every kid ever draws the sun as yellow. And there's a reason for that. Because the sun actually kind of does look yellow on Earth. Even though we know that it's emitting every frequency of light, it's emitting reds and blues and greens, and all of those add together to make white, when you're sitting on the Earth, it actually does kind of look yellow. And there's a reason. Well, the sun is actually, truly, we do know that it is emitting all of the colors of light. So it's emitting some reds, and it's also likewise emitting some greens, and it's also emitting some blues. But here's what happens, is that as that blue is coming down towards you, a lot of that blue actually ends up getting, whoa, that is a huge eraser, and I would not like an eraser that big. Get smaller, please, eraser, thank you. A lot of that blue ends up getting scattered, and so a lot of the blue actually never really makes it down to you because the blue gets scattered throughout the rest of the sky. That means that the only two colors that actually make it down to you are green, oh, I'm still on eraser mode, are green here, and red here. And if the only colors from the sky that are getting to you are greens and reds, or from the sun that are getting to you are greens and reds, then the sun is going to look like a power combo of green and red, and it's going to look yellow. This gets even more extreme when the sun sets in the sky, because when the sun gets lower and lower on the horizon, then the sun ends up over here. The sun, once again, is still emitting various frequencies of light. It's still emitting reds that are on their way to you. It's still emitting blues, which are on their way to you. And it's still emitting greens, which are on their way to you, except in the evening time when the sun is nice and low on the horizon, that light has to make it through so many more air particles all the way just to get to you. So the blues get scattered pretty quickly by all of the little air that's all in between you and the sun. So the blues get scattered and the sky around looks very blue. Then after the blues get scattered, because it has to go through so many air particles, a lot of the greens also end up getting scattered. And so less green light makes it to you and more green light ends up in the sky. As a result, it's only a little bit of green and a lot of bit of red that makes it to you from the sun. And so the sun doesn't look quite as yellow. It actually looks more of an, sorry, I need a marker. It actually looks more of an orangey kind of color because it's mostly, ooh, let's make it, oh yes, wow, color artist right here. This is just true artistry. Yes, okay. The sun looks more of an orangey kind of color because it's mostly the reds that make it through to you and some of the greens, but a lot less of the greens than when it's directly overhead. Now here's something that's true, is that here in Colorado, the sun actually can't get that low in the sky because we have these mountains that block you. But in other states, the sun can get even lower on the horizon. So in other states, the sun gets even more red. Here it gets kind of a yellowish, a dark yellowish color. If it gets down behind the mountains, it gets even more red. And if there are even more particles in the air, like if it's very humid there, then you get even more scattering. Oklahoma does not have a lot to boast about, but their sunsets are beautiful because that sun can dip so low on the horizon that you get tons of scattering of colors. Plus you have so much more humidity in the air, so you get way more scattering. So the sun looks super, super red or a really, really dark orange, and you get these beautiful, beautiful colors at the sunset because of how much scattering there is. That makes the sun look very, very red to you because the light from the sun is coming to the only frequency of light that really makes it from the sun is the red light. This also makes the sky look more cyan colored because the blues are getting scattered and the greens are getting scattered. Next sunset, pay attention. Look out on the horizon and you'll see that the sun looks like more of a yellowish color. It looks more of a yellowy kind of orange. And then as you look around, you'll see that the sky around the sun is more of a cyan kind of color. Cool stuff there, yeah? Now let's talk a little bit about clouds. When you look up at the sky and you see a cloud, that cloud appears to you to be white. Why? Well, because all clouds are made up of water droplets, and those water droplets are not all the same size. You have teeny tiny water droplets, and some medium-sized water droplets, and some large-sized water droplets. And each of these water droplets has different resonance frequencies, different frequencies of light that it scatters. Now, at any given point in time, white light from the sun is coming into this cloud. So you have red light coming into the cloud, and you also have green light coming into the cloud, and you also have blue light coming into the cloud at any given point in time. And let's draw some blue light in here. However, not all of these water droplets will interact with the light in the same way. The really small water droplets are like teeny tiny bells, and they'll vibrate back and forth like teeny tiny tuning forks, and when they do, they'll scatter the higher frequencies. So the small water droplets will scatter higher frequencies like blue. The medium-sized water droplets will scatter medium frequencies like green. And the big water droplets, because they're so large, they'll scatter the lower frequencies, like red. So because you have small water droplets scattering high frequencies, medium water droplets scattering medium frequencies, and big water droplets scattering the low frequencies, you get an even scattering of red and green and blue, which all together, as we know, make white. And so clouds look white. That is to say, when the water droplets are small enough to scatter light. If the water droplets get so big that they're not resonating and scattering light anymore, but instead they're absorbing the light, well, then the cloud doesn't look white anymore. It looks the color of absorption, which is black, because it's letting no light get out. This is how you know that it's about to rain, because the water droplets are too big to keep scattering light, And they're also too big to stay in the sky, so those water droplets will fall down straight towards the earth. Both why the sky is blue and why clouds are white, and even why the sun is yellow during the daytime and kind of an orangey red at sunset, all of those questions can be answered with the word scattering. It's all about different molecules resonating, or their little electrons vibrating back and forth, and then when they do, throwing that color out into the world. But our next question, which is why are pools cyan colored, this one has a little bit more to do with absorption. I'm going to grab a new little drawing pad here. Okay. Now here's the truth. This was always very confusing to me as a child, because when I was a little kid, I remember doing this thing that was just really strange and confusing to me, where I'd scoop up some water out of the pool and I'd look at it, and that water that I just pulled out of the pool was totally clear. But then I drop it back into the pool and I look at all the water in the pool, and all the water in the pool together is cyan colored. Or if you go to the ocean, same thing happens. You get the tide coming in, the waves crash over your feet, and the water that crashes over your feet is clear. But then you walk out a good distance into the ocean, you look down, and the water below you is like a bluish kind of color. And so this is always very mysterious. Why does a little bit of water look clear, but a lot of water looks blue or cyan colored? Always very, very strange. Now, please, do not believe the lies that have been circulating around the communities for centuries. I have heard students say things like, oh, well, the ocean is blue because it reflects the sky. Or worse, the sky is blue because it reflects the ocean. Here in Denver, Colorado, you think the sky is blue because it's reflecting the ocean? What ocean is it reflecting? No, the sky is not blue because it reflects the ocean, and the ocean is not blue because it reflects the sky. That's not at all why those things are true. It has to do with absorption of light. Here's the truth, is that water molecules are actually very good at absorbing infrared light. And the reason why they're so good at absorbing infrared light is because they have these little hydrogen bonds that require a lot of energy to break. So when infrared light, which by the way is heat, when infrared light or heat comes into the water, it breaks those little molecules apart, those little hydrogen bonds, and then they just kind of form back together again. And so you can dump a ton of infrared light, a ton of heat into those things, and they'll just keep breaking and reforming those hydrogen bonds over and over and over again. This means that because water is so good at absorbing infrared light, it also happens to be very good at absorbing red light, since infrared and red are right next door neighbors on the electromagnetic spectrum. This makes water great at absorbing red light. And so if you have a lot of water, it can absorb a lot of red light. But if you have just a little bit of water, it can't absorb that much red light. Here's how this applies to a swimming pool. If you have a swimming pool in the summertime and you have white light coming down from the sun, that means that you have red light coming down, it means that you have green light coming down, and it means that you have blue light coming down from the sky. Well, if you have just a little bit, then the red and the green and the blue can make it through, but if you have a lot of bit of water, then the red doesn't make it very far before it gets absorbed. The green can make it a little bit further before it gets absorbed, and the blue can make it the furthest before it gets absorbed. If the bottom of your swimming pool is like here-ish, is like here-ish, then light will reflect off the bottom of the swimming pool, and green light will come up off the bottom of the swimming pool, and blue light will come up off the bottom of the swimming pool like this. And so a viewer who is looking on would see that when they look at the bottom of the swimming pool, they see that green light and blue light are both bouncing off the bottom. And they would say, wow, the bottom of the swimming pool looks cyan. However, the red light would never make it to the bottom of the swimming pool, so there would be no red light for the bottom of the swimming pool to reflect. Here's a question for you. What does a red fish look like deep under the water? Did you say it looks black? For sure. There's no red light that makes it down deep to the water for the red fish to reflect. And so it'll absorb the colors green and blue, and it'll appear black. This is also why as you go, if the water gets deeper and deeper and deeper, it gets bluer and bluer and bluer. Because if it's just some shallow water, it'll look a little more cyan, but if it gets really, really deep, then all the red will get absorbed and all the green will get absorbed, and only the blue, only those high frequency wavelengths will be able to make it through. And if you get deep enough under the water so that not even the blue can make it through, well then at the very depths of the ocean we got black because there's no light that can make it all the way down to the bottom. So that's a little bit about why swimming pools are cyan. Today we answered, oh gosh, that is not what I wanted. Let me try again. Today we answered 3 important questions. First, why is the sky blue? Then, what makes the sky different shades of blue? Then we talked about why the sun is yellow, and we talked about why the sun gets a reddish orangey kind of color at sunset. We also talked about why clouds are white, and last we talked about why swimming pools are cyan. And that's about all for today, folks. I hope you have a wonderful, wonderful rest of your day and that something very colorful happens to you. Bye, good people.